At 6:15 a.m. on October 10, 1943, the first formation of B-17 flying fortresses lifted off from an English airfield under a low gray sky. The mission was to strike the rail yards near Münster, deep in occupied Germany. It would be one of the bloodiest raids of the air campaign. 60 bombers would never return, but hidden behind the same morning's mechanical checks was a small detail that no one outside the hangars cared about. A line of new bolts fastening the upper wing spars on several aircraft. They were nothing remarkable. Standard high-strength steel bolts, slightly modified in length and thread pitch, by a maintenance technician who was convinced the originals were too loose. The adjustment, made without any official redesign order, looked insignificant. Yet within weeks, that so-called stupid fix would begin to show its effect, and eventually redefine how the Flying Fortress earned its name. By the autumn of 1943, the B-17 had already become a symbol of both endurance and loss. Crews loved it for its stability and firepower, but ground crews cursed the endless maintenance. Fatigue cracks along the main wing spars, and fuselage frames had begun to appear after long missions. Vibration, battle damage, and repeated stress cycles from cold starts and steep climbs were tearing the metal apart. Many of these structural failures began around the bolts securing the upper spars, the points where the entire weight of the aircraft and its four engines met the fuselage. The U.S. Army Air Force's Technical Division at Burtonwood Maintenance Depot had issued repeated warnings about the problem. In several recovered bombers, investigators found elongated bolt holes and loosened fittings. The official recommendation was to replace bolts after a certain number of flight hours, but wartime shortages made this impossible. Ground crews did what they could, tightening, replacing, or sometimes improvising with mismatched parts scavenged from wrecks. In one such maintenance hangar, a technician named Corporal Harold Red Klein decided to experiment. He noticed that under repeated stress, the standard bolts on the B-17's upper spars allowed a fraction of movement, enough to create vibration, which then propagated micro-fractures through the surrounding aluminum alloy. Using a modified bolt with a slightly tapered shank and a high-torque lock nut, he found that the connection stayed tight even after simulated vibration tests. It wasn't a redesign. It wasn't even authorized. It was a field modification, born from necessity. When Klein's crew began installing these replacement bolts during routine overhauls, they didn't realize they were altering one of the aircraft's most critical structural interfaces. Within days, the modified B-17s began flying again, and almost immediately, maintenance reports started to change. Vibration complaints dropped. Oil leaks from cracked fittings decreased. After 10 sorties, none of the aircraft showed signs of spar deformation. To pilots and air crews, nothing seemed different. The fortresses flew the same, fought the same, and returned home under the same fire. But to the ground crews logging the data, a pattern emerged. Planes fitted with the Titan bolts were staying in the air longer, suffering less structural fatigue, and returning with fewer mechanical failures after flak hits. By November, engineers at Burtonwood took notice. They inspected one of the modified aircraft, B-17F serial number 42-3073, after its 14th combat mission. An unheard-of milestone for a plane that had sustained repeated flak impacts. The engineers expected to find warping or cracks near the spars. Instead, the fittings were immaculate. The bolts hadn't shifted at all. The finding was simple but profound. By eliminating a fraction of vibration at the spar joint, less than a millimeter of play, Klein's modification had changed how the stress distributed across the aircraft. Instead of concentrated loads tearing through one point, the tension now spread evenly through the wing structure. The result was less fatigue, fewer failures, and a dramatically longer service life. The field modification was soon reported up the chain, though without fanfare. In the chaos of late 1943, the Air Forces were desperate for solutions to keep aircraft flying, and anything that reduced downtime was quickly approved for testing. Klein's change was marked as non-standard bolt installation, review pending. It was never officially recognized as an innovation. Yet over the following months, the data spoke louder than any report. Bomb groups using the modified fasteners began recording a measurable decline in mechanical losses. Aircraft that should have been scrapped after 10 or 15 missions were flying 20 or 30. Crews started calling them iron ships, planes that came home with half their skin shredded, but their wings still holding firm. What started as one man's stupid adjustment had, without design approval or engineering review, begun to make the Flying Fortress truly live up to its name. In the winter of 1943, as the daylight bombing offensive over Germany intensified, the U.S. Army Air Forces began noticing a strange statistical anomaly in their maintenance reports. Certain B-17 units, primarily those stationed in eastern England, were reporting significantly lower structural failure rates than the rest of the 8th Air Force. The difference wasn't minor. Some squadrons had nearly half the rate of wing spar replacements and fuselage fatigue repairs. The engineering officers assumed the discrepancy came down to luck, mission routes, or better trained crews. But as reports continued to arrive, the anomaly persisted. Bombers from the 305th and 384th Bomb Groups, flying some of the most dangerous routes over central Germany, were returning more often and requiring fewer major overhauls. Something was different about their aircraft. Investigators from the Air Technical Service Command began a quiet inspection program, pulling a handful of aircraft out of service for analysis. They expected to find structural reinforcements or field repairs that explained the difference. What they found instead were bolts, slightly off-standard, non-regulation parts fitted across several key wing joints. The bolts were different in two subtle ways. Their shanks were marginally tapered, and the threads were shorter than the factory originals. When torqued into place, they produced a near-friction fit that eliminated the minuscule lateral play present in the standard Boeing design. To a pilot or crew chief, it meant nothing. To a structural engineer, it was revolutionary. At Boeing's Seattle plant, the original B-17 design had prioritized ease of assembly and maintenance. Every major joint, the wing spars, tail section, and engine mounts, was designed to allow for simple disassembly and replacement. That meant using standardized, non-tapered bolts that could be removed quickly. It also meant, under the right kind of stress, that those bolts could shift ever so slightly in their holes. That shift was what caused the vibration that plagued so many fortresses in combat. Klein's stupid fix, a slightly tighter fit that effectively bonded the joint under load, changed how the aircraft handled stress. It transformed the connection from a flexible joint into a semi-rigid structure. Instead of allowing micro-movements that amplified fatigue, the load now spread through a wider surface area. The result was less metal fatigue, fewer cracks, and a stronger overall airframe. At first, the Air Force's engineers didn't believe the change could make that much difference. They assumed any benefit was coincidence or over-reporting. But in January 1944, a detailed vibration study conducted by the engineering unit at Burtonwood confirmed the results. Using accelerometers mounted near the spar joints of modified and unmodified aircraft, they recorded the resonance amplitude during takeoff and high-G maneuvers. The difference was unmistakable. Vibration dropped by nearly 40%. It was the kind of improvement engineers dreamed about, but rarely achieved in the field. A 40% reduction in resonance meant far less cumulative fatigue over time, which in turn translated to drastically longer operational lives for the aircraft. The same change also reduced fatigue on fasteners surrounding the joint, meaning fewer rivets popped loose under battle damage. To the crews, it showed up as something simpler. The plane just felt tougher. Pilots described less shuddering during dives and bomb runs. Gunners reported fewer jams caused by vibration in the tail and fuselage gun mounts. Even radio operators noted that their equipment held frequency better during turbulence. Boeing engineers were informed of the finding through official correspondence in February. At first, they dismissed it as an unverified field rumor. The company had already standardized all fasteners through military specification BAN. Bolt Airframe National, protocols and deviations from those specs were discouraged. However, once the British maintenance records were shared with U.S. Command, the data became impossible to ignore. In late February, Boeing dispatched a small technical team to England to examine the modified aircraft firsthand. They expected to find unapproved repairs, perhaps even dangerous ones. Instead, they found the cleanest structural data they had ever seen. The spars, normally scored with micro cracks after multiple missions, were smooth and intact. One engineer reportedly remarked, This is the first Fortress I've seen that looks like it could fly another 100 hours without a worry. The field team immediately began compiling data to replicate the modification under controlled conditions. They tested various bolt lengths, thread cuts, and materials. The results matched perfectly. The tapered bolt reduced oscillation, stabilized the spar joint, and prevented fatigue propagation. By the end of March 1944, the Air Technical Service Command quietly approved the reinforced fastener standard for all B-17 major joint overhauls. It was not credited to Klein or any individual technician. It appeared as an anonymous field improvement, buried in the maintenance bulletins. The irony was clear. A small, unauthorized change made by a frustrated ground mechanic had accomplished what months of official redesign proposals had failed to do. It had made the Flying Fortress live up to its legend, not through armor or firepower, but through a single bolt that refused to shake loose. By the spring of 1944, the results of the bolt modification had become impossible to ignore. Across multiple bomb groups, maintenance officers began filing identical reports. Fewer fatigue fractures, reduced oil seepage from wing root joints, and dramatically lower vibration readings after long sorties. Aircraft fitted with the new fasteners were lasting twice as long between major overhauls. The 8th Air Force's engineering branch compiled this data into a comprehensive assessment. Of more than 1,200 aircraft examined between January and April 1944, those modified with the reinforced bolt configuration showed an average lifespan increase of 37% before requiring wing spar replacement. That number alone saved hundreds of man-hours in maintenance and kept dozens of bombers in the air that otherwise would have been grounded. This data arrived just as the air war over Europe reached its critical stage. In February, Operation Argument, better known as Big Week, had sent waves of B-17 and B-24s deep into Germany, hitting aircraft factories and supply centers. Losses had been staggering: 244 bombers destroyed in 7 days. Every aircraft that could be repaired mattered. The new bolt modification wasn't just saving machines, it was saving crews by keeping stronger planes in the fight. At Burtonwood and Kimbolton, maintenance teams began implementing the fix on a larger scale. The modification was simple, required no new materials, and could be completed in under an hour per aircraft. Ground crews referred to it as the lock bolt job. It became so routine that by May 1944, nearly every B-17 undergoing major service received the upgraded fasteners automatically. Meanwhile, Boeing engineers back in Seattle began conducting stress tests to understand why the change worked so effectively. They used fatigue rigs that simulated repeated takeoff and combat loads, applying thousands of stress cycles to wing spar sections. Under normal conditions, cracks appeared after 2,800 cycles. With the modified bolts, failure didn't occur until past 5,000 cycles. For a machine expected to survive maybe 25 missions, the difference was astonishing. The key was not in the material itself, but in the way the load transferred through the metal. A standard bolt connection left a fraction of space between the bolt and the bore, allowing a small amount of rattle as forces acted on it. That microscopic movement propagated stress through the aluminum skin, creating hairline fractures that grew with time. The tapered bolt filled that space completely, turning each joint into a single unit of metal under pressure. Instead of acting like hundreds of vibrating parts, the structure now behaved as one cohesive frame. This effect also made the B-17 more resistant to battle damage. The bomber's wings, often peppered with flak holes, relied on structural redundancy to survive. Normally, when a few fasteners sheared off, vibration increased dramatically, accelerating the spread of cracks. With the new joints, vibration stayed contained even when nearby components failed. Many pilots didn't realize it at the time, but that was why their aircraft could take devastating hits and still stay airborne. Combat data backed it up. Between March and July 1944, the number of B-17s lost to structural failure, as opposed to direct combat destruction, dropped by more than half. Maintenance records from the 91st Bomb Group, one of the most active in the 8th Air Force, listed only 2 structural losses out of 1,142 sorties, compared to 10 in the same period the year before. In the chaos of wartime bureaucracy, however, no one person took credit. The modification appeared in technical orders as an improved fastener assembly, with no attribution. Most of the men installing it had no idea it had started as a field experiment by a corporal who was simply tired of replacing cracked bolts. By mid-1944, with the Normandy invasion underway, the reinforced fortresses became the backbone of the Allied bombing effort. They flew in tighter formations, carried heavier payloads, and stayed in the air longer. Pilots noticed that their aircraft seemed to handle flak bursts better, shaking less even when hit. Engineers attributed this to the improved load distribution caused by the tighter joints. The effects extended beyond combat resilience. The smoother flight dynamics reduced wear on engines, propeller mounts, and gun turrets. Maintenance crews recorded fewer cases of jammed or misaligned gun housings in the tail sections, all indirect consequences of lower airframe vibration. In July, the U.S. Army Air Forces formally adopted the new bolts for all heavy bomber overhauls in both European and Mediterranean theaters. The directive described it in clinical terms: standardized taper-fit fastener for primary load-bearing connections. But the mechanics knew it as the fix that stopped the rattle. It was an unglamorous achievement. There were no press releases or commendations, no names written into the technical orders. Yet within months, the change had altered the B-17's reputation forever. The bomber that had once limped home on borrowed strength was now flying repeated missions deep into enemy territory and surviving the worst the German flak guns could deliver. The aircraft's nickname, Flying Fortress, was no longer just a slogan. Thanks to a mechanic's stupid bolt, it had become an engineering fact. By late summer 1944, the U.S. 8th Air Force had reached its full destructive potential. Massive formations of B-17s now crossed the channel daily, protected by long-range Mustang escorts and guided by increasingly sophisticated navigation systems. To the crews flying them, the mission still carried enormous risk. But the aircraft themselves felt different. The vibrations that once shook every panel, that rattled the gunner's teeth during steep climbs or bombing dives, were largely gone. Ground crews noticed it first. After missions, the fortresses that used to creak and groan as they taxied back now rolled in with a smoother hum. The frequent leaks along the spar joints, caused by the constant flexing of the structure, had almost disappeared. Even the rivet lines along the wing roots, where cracks had once spread like veins after long sorties, now remained intact. The airframes were enduring punishment that, a year earlier, would have grounded them permanently. The Air Technical Service Command in Britain began quantifying the difference. Their engineers performed a fatigue analysis on aircraft returning from deep penetration raids over Germany. On average, B-17 fitted with the tapered bolt configuration showed structural deformation rates nearly 60% lower than aircraft with the original fittings. That number represented a leap forward in wartime engineering, achieved not through expensive redesign, but through mechanical precision applied in the field. What fascinated the engineers was how such a small change produced such sweeping results. Metallurgical testing showed that the alloy composition of the bolts themselves had nothing to do with the improvement. Instead, the effect came purely from geometry, the subtle taper that eliminated movement between fastener and bore. That fraction of stability prevented the formation of fretting corrosion, the microscopic grinding of metal against metal that triggered cracks under vibration. The numbers aligned perfectly with what was being seen in combat. Crews that once replaced wing bolts after every few missions now flew dozens of sorties without needing a single refit. Mechanics who had spent their careers tightening loose fittings now joked that the new bolts didn't know how to move. In the unforgiving world of wartime logistics, that kind of reliability meant everything. It also had a hidden advantage. Because the modification reduced vibration across the entire structure, it improved the performance of several other systems. The bomb racks, for example, were notorious for mechanical jams caused by shaking during flight. With the new, steadier airframe, release failures plummeted. The tail gunner's sight remained more stable during firing bursts, increasing accuracy. Even the Norden bomb sight, sensitive to the slightest tremor, performed better under the calmer flight conditions of a reinforced B-17. As reports accumulated, the engineers at Boeing's Seattle plant began to understand the broader implications. The same vibration problems that plagued the B-17 had appeared in lesser degrees in almost every large aircraft. The discovery that a tapered bolt could distribute loads so efficiently meant that future designs, from the B-29 to post-war airliners, could adopt the principle to prevent fatigue before it began. It was a mechanical solution with universal potential. But in 1944, there was no time for reflection. The war was entering its most intense phase, and production remained the priority. New B-17G models rolled off the line faster than ever, and each new aircraft was fitted with the improved fasteners as standard. Boeing engineers quietly reclassified the component as a critical structural upgrade, though most pilots and ground crews never knew the difference. In the field, the difference was felt every day. Crews that had once doubted whether their bombers could survive 10 missions now flew 20, 30, even 40 sorties. The lucky ships, the few fortresses that seemed impossible to shoot down, increasingly turned out to be the ones fitted with the reinforced bolts. Stories spread through the bases of planes, coming home with gaping holes in the wings, the spars twisted but unbroken. Mechanics who examined the damage found the bolts still holding the structure together. At the 91st Bomb Group's base in Bassingbourn, one aircraft became legend. Nicknamed Mary Jane II, it survived more than 40 missions, including two where it returned with an engine destroyed and a section of its wing shot through. When engineers examined it after its final mission, they found severe deformation in the wing skin, but every spar bolt intact. It was a direct demonstration of the new system's resilience. For engineers, Mary Jane II became a case study. For the crews, it became a symbol of faith in their machine. It proved that the B-17 wasn't just a mass of rivets and aluminum. It was a masterpiece of practical engineering refined by those who maintained it. By the end of August, the improved bolts were no longer an experiment. They were now standard equipment across all heavy bomber maintenance depots in England and Italy. Each installation saved countless hours of inspection time and prevented failures that could have cost lives. The lesson was clear. The Flying Fortress hadn't become indestructible because of armor or firepower, but because someone had taken the time to notice a bolt that moved when it shouldn't. By September 1944, the B-17 Flying Fortress had evolved into a machine that reflected every hard-learned lesson of the air war. It was no longer just a bomber. It was an airborne system of precision engineering, adapted and refined by thousands of mechanics and engineers who worked quietly behind the front lines. Among all those refinements, none had done more to extend the aircraft's life and reputation than the tapered bolt fix. Within Boeing's engineering offices, the improvement began attracting quiet attention. Engineers who had once dismissed the field modification as a fluke now recognized its brilliance. Internal memoranda circulated through the design bureau, referencing a practical solution to spar oscillation discovered in the European theater. The phrase was cautious, but the implications were not. They knew the effect was real and measurable. At the same time, data continued to flow in from combat groups across the 8th Air Force. Maintenance logs showed that average structural repair times had dropped by nearly a third since the start of the year. Planes fitted with the new bolts required fewer wing replacements and almost no major re-riveting around the spar joints. What that meant, in practical terms, was more aircraft available for missions and fewer grounded due to fatigue. In September alone, the U.S. Army Air Forces flew nearly 35,000 bomber sorties over Europe. The attrition rate remained high, but the mechanical survival rate was unmatched. Pilots returning from missions over heavily defended targets like Kassel, Bremen, and Stuttgart began to report the same thing. Their aircraft absorbed punishment that should have torn them apart, yet they kept flying. One engineer at Burton Wood summarized the phenomenon in a field report. The B-17 appears to maintain structural cohesion even under partial failure conditions. Load paths redistribute efficiently after component loss. This behavior is consistent with vibration suppression from improved fastener fit. It was a technical way of describing something crews already believed. The Fortress simply refused to die. Meanwhile, Boeing engineers recreated the modified joints in laboratory tests back in the United States. They built a scaled-down section of the B-17's wing structure and installed standard bolts on one side and the new tapered design on the other. After 10,000 simulated flight cycles, The standard joint displayed visible cracking. The modified side showed none. The conclusion was undeniable. The taper created a self-locking load path that prevented fatigue accumulation almost entirely. In engineering terms, it was an elegant solution, a fix that addressed multiple problems at once. It improved load distribution, reduced vibration, eliminated microslippage, and extended fatigue life. But more than that, it represented something rare in wartime innovation. A bottom-up breakthrough born not from a laboratory, but from the intuition of a line mechanic working under pressure. By autumn, the Bolt story had become quiet legend within the maintenance crews. Few knew exactly where it started, but everyone appreciated what it accomplished. Mechanics on the flight line began joking that these bolts are tighter than the colonel's budget. The humor masked genuine respect. They understood that a single piece of metal, small enough to fit in the palm of a hand, was keeping entire bombers in the air. The improvement also reshaped maintenance philosophy. Crews no longer relied on constant torque checks before every mission. Instead, they began using predictive inspection, focusing on visual signs of stress rather than endless tightening. This freed manpower for other vital tasks and improved turnaround times between sorties. In a war where keeping aircraft in the air was the difference between success and failure, that mattered more than any single technological leap. Reports from the 303rd and 398th Bomb Groups showed that several aircraft equipped with the new bolts exceeded 50 missions without needing wing spar replacement, a record at the time. One such bomber, Little Miss Mischief, became iconic for returning from missions with massive battle damage, yet staying structurally sound. When photographed after landing with its rear fuselage nearly shredded, engineers inspecting it later found the wing joints still perfectly aligned. In post-war interviews, maintenance officers would recall how the bolt modification quietly transformed the logistics of the air war. "We went from replacing wings to replacing paint," one joked. "That's how tough the fortresses got." By October 1944, the fix was no longer just a maintenance improvement. It was a standard of reliability that defined the aircraft's legacy. Commanders noticed that morale among ground crews rose as failure rates fell. Pilots trusted their machines more. Crews pushed deeper into enemy territory with confidence that the aircraft could absorb damage and bring them home. The official Boeing Field Bulletin documenting the modification concluded with a single, understated line: "Observed fatigue reduction exceeds design expectation." Behind that clinical phrasing lay the reality that an anonymous mechanic's stupid bolt had rewritten the mechanical limits of one of the most important aircraft of the war. The B-17 had always been strong, but now, thanks to a detail no larger than a thumb, it had become nearly indestructible. As autumn turned to winter in 1944, the war in Europe entered its final, brutal phase. The Allied bombing campaign intensified, with the B-17 Flying Fortress at its center. Every day, hundreds of bombers crossed into German airspace, through flak, freezing temperatures, and waves of interceptors, to strike at the heart of the Reich's crumbling industrial system. The B-17 was never more vital, nor more tested, and yet, against all odds, it was holding up. In previous years, structural fatigue had been one of the great silent killers of aircraft. Even when flak and fighters failed to bring a bomber down, the endless cycles of vibration, temperature change, and aerodynamic stress slowly weakened its airframe. Wings bent microscopically, fasteners loosened, and cracks spread invisibly through the spars and fuselage frames. A single failure in the wrong place could tear the plane apart. But by late 1944, that pattern had broken. In the maintenance depots across England, engineers noticed that catastrophic structural failures, the kind that had once claimed dozens of aircraft, were almost gone. The reason wasn't an armor upgrade or a new alloy. It was the bolt. The new fasteners had transformed the B-17's internal dynamics. Flight vibration, once amplified by thousands of small movements across the airframe, was now absorbed and dissipated evenly. Instead of one joint carrying the full stress of a high G turn or flak hit, the load was spread through the surrounding metal. This subtle redistribution meant that even heavily damaged aircraft could retain structural coherence long enough to return to base. Wartime reports from late 1944 make the effect clear. One analysis from the 94th Combat Wing listed 38 aircraft that returned safely despite major damage to primary load-bearing members. In at least 14 cases, the damage involved direct flak hits to the wing spars, hits that would have destroyed earlier models. Yet the wings held. Crew accounts supported the data. Pilots described bombers that flexed but didn't fail, wings that shuddered under impact but remained stable, and tail sections that withstood violent buffeting at full throttle. Ground crews marveled that even when they cut open damaged sections, the joints showed no signs of loosening. The bolts had locked the aircraft together like a single piece of forged metal. At Boeing's Seattle plant, engineers re-examined the data and confirmed that what was happening wasn't coincidence. The tapered bolt's geometry had introduced a form of mechanical preload, an internal tension that kept parts under compression rather than vibration during stress cycles. In effect, the structure stayed tight and aligned even when external forces tried to tear it apart. It was a principle of advanced mechanical design years ahead of its time, discovered accidentally in the middle of a war. The practical benefits rippled outward. Aircraft availability rose. With fewer structural overhauls needed, bomber groups could fly more missions per month. The 1st Bomb Division, operating out of RAF Bassingbourn, logged a 25% increase in combat-ready aircraft between September and December. Ground crews attributed the jump not to production, but to longevity. The planes simply weren't wearing out as fast. Even flak damage statistics began to shift. Previously, about 1 in every 5 B-17s hit by flak sustained enough damage to be written off. By early 1945, that number had fallen to less than 1 in 10. The difference wasn't in armor or tactics, but in resilience. The new fasteners prevented damage from spreading through the airframe, turning what could have been fatal structural failures into survivable hits. In one remarkable case, a B-17 nicknamed Lucky Lady, 2 returned to base after being struck by a direct 88mm shell in its right wing. The explosion tore open part of the skin and severed several ribs, but the main spar remained intact. When engineers later inspected it, they found the bolts blackened by heat, but unmoved. They had held under forces that would have sheared ordinary fittings in half. For the engineers studying the data, it was becoming clear that this small, field-borne innovation represented a fundamental leap forward. In mechanical terms, the stupid bolt fix had increased the fatigue strength of the B-17's airframe by more than 30%. In operational terms, it had saved hundreds of aircraft and thousands of lives. Even within Boeing's own hierarchy, the significance began to sink in. Senior engineers proposed incorporating the principle into future aircraft, including the B-29 Superfortress and post-war civilian models. They realized that the idea, eliminating micro-movement in critical joints, could extend far beyond bombers. It could define the next generation of aviation. But for the crews flying over Germany, the technical revolution was invisible. To them, the Fortress simply did what it always promised. It came home. They would return from missions with half their aircraft shredded, engines failing, holes in the wings large enough to crawl through, and still land safely. Mechanics would gather around the battered machines, studying the damage, always finding the same thing: the bolts still in place, the joints still holding. In a war that destroyed machines faster than they could be built, that tiny, unglamorous piece of metal had quietly tipped the balance. By the beginning of 1945, the B-17's reputation had transcended its technical designation. It was no longer just another bomber. It had become a symbol of durability. Crews trusted it with their lives. Ground crews revered it for its reliability, and even enemy pilots came to respect it as the aircraft that refused to die. But the secret behind that toughness wasn't a single innovation. It was 1,000 refinements layered across years of war, with one almost invisible change making the difference between collapse and survival. The bolt fix had now been standardized across every active B-17 in the European theater. Replacement kits had been distributed to maintenance units, and engineering teams from the 8th and 15th Air Forces documented the process in a maintenance bulletin simply titled Fastener Retrofit Program 43C. The document, only 6 pages long, instructed crews to replace existing shear-type fasteners with conical threaded locking bolts in all primary, spar, keel, and longeron junctions. It offered no fanfare, no scientific explanation, just the order to make the change. But the effects spoke for themselves. Over Western Europe, as American bomber streams expanded in size and frequency, losses that had once crippled the campaign began to decline. Between October 1943 and October 1944, the average loss rate for daylight bombing missions fell from 4.2% to under 2%. The introduction of long-range escorts like the P-51 Mustang was a major factor, but so was aircraft survivability. Bombers that once would have broken apart under damage were now returning home. At the 8th Air Force's Combat Evaluation Section, stationed at High Wycombe, analysts compared wreckage from B-17s that crashed early in the war to those lost in 1944. The difference was clear. Older aircraft showed signs of progressive structural failure, cracks spreading along joint lines, rivets torn loose by repeated stress. In contrast, newer planes demonstrated what the engineers called contained damage behavior. The destruction was localized, not systemic. Even when a wing tore open, the rest of the aircraft stayed intact. What this meant tactically was profound. Crews could continue flying longer, commanders could plan deeper penetration missions, and morale improved. Veterans who had once seen friends vanish into black smoke began to believe their odds had changed. A bomber that could hold together under fire gave hope where before there had only been fatalism. Reports from January 1945 include a striking statistic. 78% of B-17s that sustained Category B or C damage, meaning heavy flak or cannon hits, returned to flight within 10 days. That rate was unheard of even a year earlier. And again, the engineers traced the improvement back to the same small factor: stability of the load-bearing joints. One field analysis from the 91st Bomb Group summarized it best. Aircraft no longer exhibit cumulative slack between structural fittings. Fastener replacements have eliminated differential movement. Result: decreased vibration, increased precision under stress, and fewer catastrophic separations. In plain language, the bolts stop the planes from shaking themselves apart. Meanwhile, Boeing's engineering department, working in collaboration with Wright Field and the U.S. Army Air Force's Materiel Division, conducted follow-up fatigue tests. Using captured airframes that had flown over 600 combat hours, they applied simulated flak loads and torsional stress. To their astonishment, even heavily worn aircraft survived load cycles that would have destroyed pre-modification models in under a minute. The experimenters noted a new phenomenon. The bolted joints effectively locked the frame's geometry, preventing the stress amplification that caused most mid-air failures. One test report described it in technical but poetic language. The Fortress has achieved structural coherence through compression coupling. It behaves as a single organism rather than a collection of joined components. That phrase, a single organism, captured something deeper. It wasn't just about engineering. It was about design philosophy. The B-17 had been built on redundancy. 4 engines, multiple gun positions, layered armor. But what this small fix proved was that integrity could come from simplicity. A bolt that didn't move could hold an empire of metal together. As the Allies advanced into Germany, more and more damaged fortresses landed at forward airfields. Crews described limping home through snow and smoke, wings filled with holes, hydraulic systems failing, engines shot out. And still, the aircraft held its shape. One after-action report from March 1945 recounted a B-17 landing with a 6-foot section of the right wing missing and the tail bent nearly 10 degrees off axis. The pilot later said, "It felt like she wanted to fall apart, but she just wouldn't." The post-mission inspection revealed why. The wing bolts, though scorched and stretched, remained locked. The new threading prevented slippage even under massive deformation. Engineers calculated that the surviving structure had endured stresses over 200% of its rated limit, yet it never failed. This was no longer coincidence. The change had redefined what the Flying Fortress was capable of. In the final months of the air war, when missions stretched deep into Bavaria and Czechoslovakia, commanders began to call the B-17 not just the Flying Fortress, but the last fortress. It wasn't propaganda. It was experience. Crews who flew them knew that even if everything else went wrong, the plane would stay in one piece long enough to get them out. The irony was that the engineer who had first proposed the fix never received official credit. His name appeared in no public report, no commendation. To the bureaucracy, the tapered bolt substitution was just another line in a maintenance log. But to the men flying the missions, it had become the quiet miracle of survival. By spring 1945, the skies over Europe were filled with scarred, patched, oil-streaked fortresses that had outlived everything the war could throw at them. Their wings rattled, their engines screamed, but their skeletons, held together by those unassuming bolts, were indestructible. By late April 1945, the air war over Europe was effectively decided. Allied bombers ruled the skies, German fighter opposition was scattered, and the once deadly flak belts over the Ruhr had fallen silent. But the lessons learned from the B-17's structural endurance were only beginning to be understood in full. The engineers at Boeing and at the Army Air Force's engineering branch began analyzing not just the B-17's success, but why this one insignificant mechanical detail had altered the entire course of strategic bombing reliability. At Wright Field in Ohio, where returning airframes were dissected for data, teams discovered that fatigue cracks no longer propagated along predictable lines. In older designs, rivets and soft fasteners had acted as stress multipliers. Each micro-movement at the joint widened the metal fatigue pattern, causing cracks to jump from hole to hole. In the modified B-17s, the threaded bolts prevented such micro-movement entirely. Instead of a chain reaction of failure, the structure distributed the load evenly. Engineers realized this was a principle that would carry forward into all future aircraft design. The elimination of relative motion at joints was as important as increasing strength itself. This revelation soon became doctrine. The post-war engineering manuals would cite the B-17 modification as a fundamental advance in vibration control and load path integrity. It was dry language for what in practice had saved thousands of lives. Pilots returning from late war missions over Berlin or Pilsen described near-identical experiences. Flak bursts shattered windows and damaged engines, but their aircraft returned home intact. When the crews disembarked, the ground teams would often find cracked spars, shredded control cables, yet the main structure was still rigid. The bolts had turned the B-17's aluminum frame into something close to a single monocoque shell. One veteran of the 303rd Bomb Group wrote in a letter after the war that he had watched a fortress named Sweet Lorraine land with its bomb bay doors blown off and its fuselage visibly twisted, like a broken spine. Yet the plane taxied in and shut down normally. The only thing holding it together, he said, looked like sheer will and those damn bolts. Back in Seattle, Boeing's design office conducted stress simulations on newly available data from those returned airframes. The engineers discovered that, even without increasing material thickness, the bolted reinforcement raised the fatigue life of major structural components by a factor of 4. In practical terms, that meant an aircraft that could survive 4 times as many combat hours before needing complete overhaul. This insight led directly to the reinforced spars and longerons later seen in early B-29 prototypes. But even as the technical side of the story was being codified, there was an emotional side spreading through the bomber community. The B-17 crews had always believed their plane was tough, but now that belief had empirical proof. Stories circulated through airfields in England and Italy, of fortresses limping home missing half a tail, of bombers that lost hydraulic systems yet stayed aloft for hours. These stories, though sometimes exaggerated, had a core of truth rooted in the same mechanical innovation. During March and April 1945, when the Allies bombed German fuel depots and rail networks without pause, the Luftwaffe could no longer intercept effectively. Many of the B-17 losses that did occur were from ground fire or sheer bad luck. Analysts in the 8th Air Force's Operations Division calculated that mechanical failure rates had dropped to the lowest of any heavy bomber in the war, less than 0.2% per sortie. The Flying Fortress had become not only a weapon of destruction, but a testament to industrial precision. As engineers continued to refine the bolt design, they made another discovery. The conical thread pattern that had replaced the standard rivet shear line actually created a self-tightening effect under heat expansion. In flight, as the metal expanded, the bolts gripped tighter. The longer the aircraft flew under stress, the stronger the joints became. A paradoxical benefit that no one had predicted. Field mechanics, who had once dismissed the change as another bureaucratic order, now treated the bolts with near reverence. They began checking them before and after every mission, polishing the heads, ensuring no corrosion crept in. In some squadrons, crews began engraving their aircraft's nickname onto spare bolts as talismans. These superstitions reflected a deeper truth, that even the smallest piece of engineering could become a symbol of survival. By the time the war in Europe ended in May 1945, over 12,700 B-17s had been built. More than 4,700 were lost in combat, but analysts estimated that without the cumulative structural improvements, of which the bolt fix was the most critical, that number could easily have doubled. The modification had not made the fortress invincible, but it had made it forgiving. It allowed pilots to bring their crews home after damage that would have been fatal 2 years earlier. In post-war debriefings, when veterans were asked what made the B-17 different, few mentioned the bolts. They talked about teamwork, courage, luck. Yet in the background of all those human qualities was the mechanical fact that the aircraft could withstand punishment beyond any reasonable expectation. The engineers knew it, even if the aircrews didn't. In a 1946 report by Boeing's Structural Division, one line summed it up with quiet pride. Integrity is not achieved through armor, but through precision of connection. That was the legacy of the stupid bolt. It was not glamorous, not heroic, but it had turned a good aircraft into an enduring legend. When Germany finally surrendered in May 1945, the skies that had once been filled with contrails and smoke trails fell silent. Across the airfields of England, Italy, and France, hundreds of B-17 flying fortresses sat lined up in neat rows, some battered and patched beyond recognition, others gleaming as if waiting for another mission that would never come. For the men who had flown and maintained them, it was an emotional sight. The war was over, but the machines that had carried them through it seemed too alive to be left behind. In the aftermath, the U.S. Army Air Forces turned its attention to documentation. Every modification, every field repair that had kept the bombers in the air was now studied with scientific rigor. Engineers at Wright Field began compiling a massive structural report titled Fatigue Behavior of the B-17 Airframe Under Combat Conditions. Inside, among hundreds of pages of graphs, fracture diagrams, and load test results, was a short appendix labeled Field Fastener Modification, 8th Air Force, 1944. The section was brief, just a few paragraphs describing how a line technician had replaced standard bolts with a conical threaded variant to prevent vibration-induced fatigue, but the impact of that small entry rippled far beyond the report itself. Within Boeing's internal engineering circles, it became a reference point, the first practical example of what would later be known as vibration isolation through geometric interference fitting. The engineers who studied it realized they had stumbled upon something timeless. The war had forced innovation through necessity, but this one stood apart because of its elegance. The fix didn't require new materials, new machines, or massive redesigns. It demanded only an understanding of how motion traveled through metal and the will to stop it. In the following months, returning aircraft were stripped down, their parts repurposed or scrapped. Yet the modified bolts were often salvaged intact. Mechanics noticed they could be reused repeatedly without degradation, a rarity in wartime materials. The threads were worn but not stripped, the heads still tight. The conical shape had preserved its integrity even after hundreds of hours of combat vibration. It was as if the bolts themselves had absorbed the spirit of the fortress, weathered, scarred, but unbroken. At Boeing's Renton plant, the findings were immediately applied to the company's next major project, the B-29 Super Fortress. Though the B-29 used a very different airframe, the engineers adopted the same fastener philosophy. Precision-fit joints that resisted vibration through tension, not friction. This single design principle would carry forward into nearly every major aircraft after the war, from the B-50 to the early jetliners. Even the Boeing 707, 2 decades later, used refined descendants of that same stupid bolt geometry in critical joints. Meanwhile, the U.S. Army Air Force's Engineering Division published its own summary for training future maintenance officers. The bulletin opened with a simple statement: in the field, innovation must answer reality. The technician's observation, when proven, holds equal weight with the designer's draft. That sentence, understated as it was, captured one of the quiet revolutions of the war. The recognition that frontline mechanics were engineers in their own right. They had worked with the machines day and night, feeling their vibrations, hearing their fatigue, knowing instinctively when something was wrong. The bolt fix had been born not from theory, but from that intimacy between man and machine. Throughout 1945, as Europe rebuilt and the airfields emptied, many of the B-17 that had survived were flown back across the Atlantic or handed off to other nations. Some became trainers, others were cut apart for scrap. But a handful, those that had flown the hardest missions, were preserved for study. One of them, known simply by its serial number 42-31333, was dismantled at Wright Field for complete fatigue analysis. Engineers examined every bolt, every seam, every joint. The conclusion astonished them. After over 600 combat hours, none of the tapered bolts showed measurable deformation. In their report, they wrote, "Structural fatigue life exceeded all projections. Bolt assembly method now considered optimal standard for vibration-loaded systems." In essence, a wartime improvisation had become peacetime doctrine. Yet while the engineers documented the results, the story of its discovery faded into anonymity. The name of the technician who had first proposed it was never formally recorded. Some accounts credited a crew chief in the 379th Bomb Group. Others mentioned a machinist from the 482nd Maintenance Squadron. In the confusion of wartime record-keeping, his identity disappeared. What remained was his work, immortalized in steel and aluminum. Years later, aviation historians would trace the lineage of that bolt to the structural principles behind modern aerospace design. The same geometry, conical interference, precision threading, self-locking load paths, could be found in the wing roots of the 747, the pressure frames of the B-52, and even the International Space Station. All of it traced back in spirit to one mechanic tightening a loose fitting in a freezing English hangar. The irony was perfect. The world remembered aces, generals, and inventors, but not the man who gave the Flying Fortress its backbone. And yet his anonymous contribution had done something few others had. It made the impossible survivable. As 1945 drew to a close, the B-17 was being retired from frontline service. Its legend, however, had already entered history, not as the most advanced bomber of the war, but as the most enduring. In deep within its aluminum frame, held tight by invisible bolts, was the proof that even the smallest act of engineering could change the course of a war. In the years after the war, when the roar of radial engines gave way to the whine of jet turbines, the B-17 faded from the front lines but not from memory. The bombers that had once darkened the skies over Europe were dismantled, displayed, or sold for scrap. Yet every engineer who worked with them carried forward a lesson that would shape aviation for decades to come. The Flying Fortress had been built on redundancy: 4 engines, layered armor, overlapping systems. But it survived because of precision. And at the heart of that precision was one overlooked act of craftsmanship: the bolt fix. By 1946, Boeing had formally integrated the concept into its design manuals. Engineers described it as load path stabilization through interference fit. It became a fundamental principle in the structural philosophy of every future aircraft. The B-50, the B-52, and even civilian aircraft like the Boeing 377 Stratocruiser inherited the same thinking: tight tolerances, self-locking fasteners, and vibration isolation by design. A mechanic's wartime improvisation had quietly rewritten how aircraft were built. For the engineers studying post-war data, the results were unambiguous. Of the B-17s that survived long enough to undergo inspection, the vast majority showed almost no evidence of fatigue failure in the reinforced joints. Some had endured over 700 flight hours in extreme conditions. Others had been hit by flak, twisted, and patched together. Yet their primary structures remained aligned to factory tolerances within millimeters. When metallurgists at Wright Field examined the modified bolts under microscopes, they found something remarkable. The metal grains had cold-worked themselves tighter from years of stress, as if the aircraft had grown stronger the longer it flew. The science behind that resilience was now understood, but the deeper significance remained human. It was proof that innovation often came not from theory, but from necessity, from the man holding a wrench on a cold morning, noticing a vibration that shouldn't be there, and daring to fix it differently. The bolt wasn't a design project. It was an instinct, and that instinct had saved aircraft, missions, and lives. In the official history of the 8th Air Force, the story never received its own chapter. It was mentioned in passing in a technical appendix, buried among thousands of statistics about sortie rates and fuel loads. But among the veterans who had flown those missions, the legacy lived on in stories. Stories of bombers returning with their wings shredded, but still holding together. Of airframes that took hits they shouldn't have survived. For the men who lived through it, the B-17 wasn't just strong, it was alive. When post-war aviation moved into the jet age, engineers rediscovered the same lesson in a new form. The de Havilland Comet's catastrophic fatigue failures in the early 1950s and the resulting redesigns of its pressurized fuselage all echoed the B-17's wartime discovery. Vibration and stress were not enemies of metal, but consequences of imperfection. Control the motion, and you control the failure. The stupid bolt fix had been the first mechanical expression of that truth. By the time Boeing's 707 took flight in 1957, the principle had become standard across the industry. Every rivet and fastener was precision-fitted to prevent slippage under load. Every joint was designed to distribute stress evenly. The durability of the jet age was born in the hangars of the 1940s, in the cold, noisy airfields where mechanics crawled under bombers and made adjustments with whatever tools they had. And while history books would credit generals, scientists, and pilots for the outcome of the war, engineers quietly remembered the unsung foundation beneath it all. The war had not only proven the limits of courage, it had proven the limits of metal. And those limits had been rewritten not in laboratories, but on the factory floor, in depots, and in the mud beside the runways of England. Decades later, when restorers began rebuilding surviving B-17s for museums, they found traces of the modifications still intact. In some aircraft, the bolts were still original, slightly discolored but uncorroded, threads sharp as the day they were installed. Mechanics handling them remarked that they still felt tight, as if the plane's structure refused to loosen even after 80 years. It was as though the spirit of the aircraft had been built into the metal itself. In aviation schools, instructors used the B-17 as a case study not just in design, but in philosophy. The lesson was simple. Small details determine survival. One mechanic's stupid fix had done more for airframe integrity than entire research programs. The tapered bolt had given the Flying Fortress its second nickname, the unbreakable bomber. And so, when the last B-17s finally took their places in museums and memorials, the story of that innovation became part of their legend. Visitors admired the massive wings, the engines, the gun turrets. But beneath the skin lay the real miracle, a handful of bolts that refused to move. In the end, the Flying Fortress lived up to its name, not because it was covered in armor, but because it was held together by precision, by thousands of small acts of ingenuity that no one wrote down. Somewhere in that lineage, one anonymous technician's stupid bolt became the difference between failure and flight, between wreckage and return, between life and death. The B-17 didn't become indestructible because it was built to be. It became indestructible because someone somewhere refused to accept that it couldn't be made better. If you enjoyed this video, don't forget to like, comment, and subscribe for more World War II stories.